In this video, we'll take a look at meso compounds. Meso compounds are an especially difficult concept that fall under the category of stereoisomerism, so you need to understand the ideas like absolute configuration, Kahn-Ingold prelog rules, all of the things like that you need to have a good mastery of before you can really understand meso compounds. So with that, we'll jump right in. Meso compounds have three specific requirements in order for them to be considered meso. The first requirement is that the molecule must contain an even number of chiral centers. So 2, 4, 6, 8, etc. It cannot be odd. As a caveat to this, there are a few molecules that appear to have 3 chiral centers, but on closer examination they do not, so it will always follow a rule, this particular rule. Next, the meso compound must have an internal plane of symmetry. So what that means is that the chiral centers will have the exact same groups bound to them. So this will be more clear with a specific example, but some students can see the internal plane of symmetry rather quickly. Others is a little bit more difficult. So both of these will help you get to the correct idea, but you need to be able to identify the internal plane of symmetry, and it may take some practice. And lastly, then the absolute configuration must cancel within that molecule. So what I mean by that is if one chiral center is R, the other one must be S, or vice versa. If it's RR or SS and it follows the other two rules, it will not be meso. So this is rather difficult, so I think the best way to explain it is to just jump right into some specific examples. So the question here is to just identify if these are meso compounds or not. So again, let's go back through our rules. So first, it must contain an even number of chiral centers. So let's investigate that here. So what appears to be our chiral centers are these 2 carbons. So let's look at this one and make sure that it is in fact chiral. So if we look here, this is bound to a methyl group, and then a carbon, a CH2 over here, a carbon bound to another methyl group and another carbon. So that is all different groups. We have our methyl, we have this whole thing, and then this whole thing. So those are 3 different groups, and then the hydrogen, of course, is implied but not drawn. And here, this molecule, or this chiral center is the same idea. You have a carbon bound to a methyl group, bound to this whole thing, and bound to this whole thing, which are both different. So therefore, this has 2 chiral centers, and that follows that's an even number. This position and this position are not chiral. Neither of those carbons are, because they have 2 hydrogens each that are not drawn but are implied. And because of that, then these are the only 2 chiral centers. Next, then, it must have an internal plane of symmetry, or if that's difficult to see, the chiral centers must have identical groups. So there is an internal plane of symmetry, and it is right here. I'll draw a dashed line. So either side of that line has the exact same group, the exact same molecule. You have a carbon bound to a methyl and a CH2. That is the same on either side, so there's your plane of symmetry. You can also look at the chiral centers and identify that there is the exact same groups bound to them. So let's do that once more. We have a carbon bound to a methyl, bound to a CH2, CH2 methyl, and then a hydrogen that is there. And also going down here, carbon bound to a methyl, and then so on. So either way you look at it, there's an internal plane of symmetry, and all of the groups bound to both centers are identical. Okay, so that meets the second rule that it must have, or the second requirement, it must have an internal plane of symmetry. And then lastly, the absolute configuration must cancel. So we have to determine that. So I'll redraw the molecule for us to identify the priority groups in the way that they are rotating. So our chiral center is bound to a methyl group, and then this carbon over here, which is bound to another carbon, or the other group is this carbon here bound to 2 carbons. So when we put that together, this group down here is the highest priority because it is bound to 2 carbons, whereas this is only bound to 1, and then this is bound to no carbons, just hydrogens. So down here, the group down relative to this chiral center is the highest priority. Then this group here, because this carbon is bound to another carbon, where this is just a methyl group, which is bound to no carbons, just hydrogens. So that is our configuration. That looks like R. and the hydrogen is in the back, so it is R. So this top center is R. So I'll just underline that it is R for now. Now if we look at the other position, down here, we have to identify the priority groups again. So we have a methyl group, a carbon bound to 2 carbons, and a carbon bound to 1 carbon. So the group going up is the highest priority here, and then 2 is the one to the left, and the methyl group is 3. So now that looks like S. And the hydrogen is in the back, so it is S. So now this top group, so I'll redraw the molecule once more to illustrate what we have done here. So we have R at the top and S here. So now the very last rule is that the absolute configuration cancels. Well, we have RS, so that cancels. So this is in fact meso. And meso compounds are achiral. So this is not a chiral molecule. It can only be classified as meso and nothing else. It has chiral centers, but it is not chiral as a molecule. So that is a nuanced idea that is a little bit different. And also one other thing I want to mention here, molecules that are achiral are not necessarily meso, but meso are achiral molecules. So it's kind of the idea of a square and a rectangle. You have to know which one fits into which box. So that's why mesos can be very difficult because of that idea. They're so nuanced. So let's do one more example, and then we'll move into some of the more difficult questions for today. So here, now we have 2 chiral centers again. It's basically the same molecule, except chlorine is here. The internal plane of symmetry that we did have here is now broken because of the chlorine. So there is no plane of symmetry. So because of that, this right away cannot be chiral. Or sorry, cannot be meso. There are chiral centers, but it cannot be meso because there's no plane of symmetry. So also, if you struggle to see the internal plane of symmetry, then you can always look at the groups that are bound. So this carbon has a chlorine, and then the carbon with 2 more carbons bound to it, and then this carbon with 1 carbon bound to it. So that's one set. This has the methyl instead of the chlorine. That's different, so it doesn't have one of the requirements for meso compounds. So then you could continue with determining the absolute configuration, but for the sake of this question, we are interested in only if it's meso, and it's not, so that's all we need to investigate for this question. We can stop at the second requirement and say that this is not a meso compound. Okay, here we have another example. So the first thing that we want to do is go back through our rules. So the first thing to check is there 2 or more chiral centers? Is it an even number specifically? We have 2 that appear to be chiral. Upon closer examination, we have a methyl group, and then the carbon bound to another carbon, and a carbon bound to 2 carbons. So these are different groups. So this position is chiral. This is identical, so it is also chiral. All of the other positions have 2 hydrogens, so they're all not chiral centers. So that there's 2 chiral centers. That meets the first requirement of a meso compound. Next, there is an internal plane of symmetry here. It's very similar to the first example we did. And the other way you can check this is by looking at the groups that are bound there. So we have this carbon bound to a methyl, bound to the CH2, and then the carbon bound to methyl and a CH2. So those are the same on both sides. So it is an internal plane of symmetry. It meets the second requirement. Then you check your absolute configuration. So we have this carbon is very similar. So we have carbon bound to 2 carbons, carbon bound to 1 carbon, and a methyl group. So down is the highest priority. And here, then the methyl group. So that looks like R. And the hydrogen's in the back, so it is R. Now, let's do the bottom carbon, this carbon here. So if we look at this guy, we have a carbon bound to 2 carbons up, so that's our highest priority. Then this carbon bound to 1, that's the second priority, and the methyl group is the last priority. So this looks like S because it's counterclockwise. So now we have to check, is the hydrogen in the back? It is, so this is S. So now what we have is another RS molecule. We meet all other requirements for it to be meso. So it is in fact a meso compound. So this is R and this is S, so this is meso. Now you may be wondering, are all of these cyclic structures that are cis, are they meso? And it's not necessarily the case. I mean, more than often it will be the case. But consider this example. Here's one example that would break that rule as being always true. So if you look at this guy, you would say, hey, that's cis. There's an internal plane of symmetry. There's actually several internal planes of symmetry in this molecule. You could draw one across this. You could draw one across here, and so on. I'll just draw these two. But the main point here is neither of these are chiral because the groups are the same. So if we look here, we have at this center for being chiral, we have a methyl group and then a CH2, CH2, that's the same. CH2, CH2, that's the same. And then a CH bound to a methyl, we get to the same point. So this is in fact achiral and not meso. So this is a nice example to show that it's not always just a cis cyclic structure is going to be meso. You always have to go through the rules and check and convince yourself that it is meso or it isn't meso. Okay, here we have another example. So if going through our rules, we want to check if this is meso. So first rule is that we need an even number of chiral centers. So looking at this, we would think that this has 3, right? Because of the wedges imply that. But if we consider each one, we'll find that in fact it only has 2. If you look at this chiral center, or this carbon, and we're investigating if it is a chiral center, we have a bromine, a methyl group, a carbon bound to another carbon, and a bromine. Those are all different, so this position is definitely chiral. Now if we look at this one, this is a carbon bound to a bromine, bound to a carbon, bound to a carbon, so where my left hand pointing to and where the marker is pointing to, those are the same because it's a carbon bound to a bromine, and then a hydrogen there. And then if you move further, there's a CH3, CH3. So this is in fact not chiral at this position because the groups on either side is the exact same. So, and then this one is the same as the first one that we did. And so it is in fact chiral as well because we have a bromine, methyl group, hydrogen in the back, and then this whole group here is different than the other 2 groups. So this in fact has 2 chiral centers. So it may be meso. It at least meets the first requirement. Then second, is there an internal plane of symmetry? There is across this carbon. There, either side of that is the same, so internal plane of symmetry is there. Okay, and then lastly, we are to investigate if the absolute configuration cancels. So I've marked this molecule up pretty well, so I'm going to redraw it twice so we can investigate both centers. So here's our bromine, here's our bromine. Now I'm going to redraw this one without a wedge because we just found out that this is in fact not chiral at that carbon, so it doesn't need to have the dash wedge convention because it is not chiral, so it doesn't make a difference if that bromine is a dash or a wedge. It will be the same either way. Okay, so now let's determine our absolute configuration at both of those centers, both those carbon centers. So here we have a bromine. Carbon bound to the chiral center is attached to a bromine as one group. That's definitely the highest priority. Then we have a methyl and a carbon bound to another bromine. So this will be the second position, the second priority. And then the methyl group is 3. So that looks like R. And the hydrogen is in the back because the bromine is a wedge, so it is R at this first position. Okay, now let's consider this position. So we have bromine, highest priority. The carbon bound to another carbon and a bromine is the second, and then the methyl group is third. So this looks like S. And in fact, the hydrogen is in the back, so it is S. So this is RS, which the absolute configuration cancels. So this is a meso compound and is therefore achiral as well. All right, and here we have the most difficult type of problems in the meso category. So we're asked to draw the enantiomeric pair for the following molecule. So the first thing to point out is this molecule does not have a dash or a wedge on either of the OH groups. The reason for that is because we're asked to draw the enantiomeric pair, which means that we have to determine what stereochemistry must be necessary for the two molecules to be enantiomers. So basically we have to decide as the one's answering the question, if this needs to be a dash or if this needs to be a wedge or either combination. So this is a particularly tricky one because there's a potential for it to be meso. Because if we go through the rules or the requirements for meso, we have two chiral centers, we have an internal plane of symmetry here, and the absolute configuration may cancel because we only have these two centers. So depending on what we pick, the absolute configuration may cancel. So basically you have to guess and check a little bit when it's a rather open-ended question like this. And also, to answer this question successfully, we need to recall what an enantiomer is. An enantiomer is a pair or a relationship between molecules in which all chiral centers have opposite absolute configuration. So I'll just say all centers have opposite absolute configuration. So what that means is if you're going to look at two enantiomeric pair, you're going to look at two molecules that are enantiomers. The absolute configuration would have to be RR and SS in order for all the absolute configurations to be opposite to meet the enantiomer requirement. So to answer a question like this, we may have a meso compound. So we basically just have to guess or to just pick one of the stereoisomers that we could have here. So what I mean is like we get to decide, is this going to be a dash or a wedge, or if this is going to be a dash or a wedge. And then we need to check using our absolute configuration in the meso rules if it is in fact meso or not. So if we were to do this, then let's just call that this is going to be a wedge and this is going to be a dash. Since, like I just said, we have to pick. We don't get, we're not told that information in the question. So you just have to pick and then determine if it's meso or not on your own. So if we look at this, we have a OH group bound to our chiral center, so we need to determine the absolute configuration. This is the highest priority among the options bound to that carbon. Then this is the second because this is a carbon bound to an oxygen versus just a methyl group. So the methyl group is last, so that looks like R. And the hydrogen is in the back, so it is R at this position, right? Now if we look at the other chiral center, we have an OH again, that is the highest priority. Then the carbon bound to the oxygen and another carbon is the second priority. So we'll just use the same two that we did in the previous assessment. And then the methyl group will be last. So that looks like R as well, but for this second chiral center, so for second center, the hydrogen is a wedge. So it's actually S. It's actually the opposite of what it appears. So this one is S. Now if we look at our resulting molecule, this is meso, right? We have R and S, we have an internal plane of symmetry, we have two chiral centers that absolute configuration cancel, so therefore this is meso. So why this is relevant to this question is if we draw what appears to be its enantiomer, so I'll redraw this molecule and then draw its enantiomer. So here we have our wedge and our dash, and then its enantiomer would be dash and then wedge. Right? So if we do this, these are in fact identical because the absolute configuration here is R, here is S. Anytime you switch two positions for the substituents in a group, so like this is OH is a wedge, and then the hydrogen is a dash. So now the OH is a wedge, and the hydrogen would be, or the OH is a dash, and the hydrogen would be a wedge. So that is switching two positions. So this becomes S. And vice versa, this becomes R because we've converted the dash to a wedge. So the reason that this is identical is because there's no preference as where you start. So if you were trying to name this, for example, you could go 1, 2, 3, 4, or 1, 2, 3, 4. You could also rotate this molecule and find that it's exactly the same. So this can't be meso, or this is meso and therefore can't be enantiomeric. So these are identical because it's RS or SR. It's the same either direction. The reason for it, though, it's not just going to be identical because it's SR for any molecule. It's identical because there's that internal plane of symmetry as well. It needs to have both of those characteristics. So then the only thing that's left for us is if these are the same, if they're both dashes or they're both wedges. So if we were to draw that option, we get one more sheet of paper here. So if we were to draw that option that I'm referring to, you can pick again if it's going to be both dashes or both wedges. I'm drawing both wedges here, but again, it doesn't matter. Now we determine the absolute configuration. So here is 1, here is 2, here is 3. That looks like R. The hydrogen is in the back, so it is R. If we look at this one, the oxygen OH group is the highest, then this carbon, then the methyl group. That looks like R. The hydrogen is in the back, so it is R. So this is not meso. So its enantiomeric partner would be the 2 dash OHs. So if we were to redraw this, here we would have the other pair. And again, if you assess the absolute configuration, you have 1, 2, 3. That looks like R, but the hydrogen is a wedge, so that's an S. Also, we just converted a dash or a wedge to a dash, so that always inverts the stereochemistry. So here we have 1, 2, 3. That looks like R. The hydrogen's in the front, so that is S. So this is in fact the only enantiomeric pair for the starting molecule that we had, which, just for a reminder, was this one with no dash or wedge, no stereochemistry indicated at all. This is the only two possible enantiomeric pair, the only two molecules that are enantiomers. Okay, let's do one more example. Same type of question. Draw the enantiomeric pair for the following molecule. Again, the stereochemistry is not identified as dash or wedge because that's the whole point. You need to draw the molecule as an enantiomeric pair. So again, you just pick to assess a pair to see if it's meso first. That's the only thing that would be of issue here. Again, because we have two chiral centers, we have an internal plane of symmetry across those carbons there, as that is the same. And then the absolute configuration may cancel depending on which molecule we choose to draw. So let's just say that we'll pick the wedge, both wedges. Okay, so if we do that, we'll have to determine the absolute configuration at each center. So this is our chiral center, is one of them. Here, the chlorine would be highest priority. Then this CH2 group up here on the left is the same as the CH2 group here on the right. Then we move again, and it's CH2 and a carbon bound to a chlorine. So that is higher priority. So that's 2. This is 3. That looks like R. And the hydrogen is in the back, so it is R. This position is R. Then if we look at this guy, we have our highest priority again is the chlorine. Then it would be this position going up here because the difference is the chlorine at the second carbon away. So that would be higher priority. And then the group up here is 3 because it's just our CH2 group and it's further away from the chlorine. So that looks like S. Oops, looks like S, right? Because it's going counterclockwise. It is in fact S because the hydrogen is in the back. So this is also a meso compound. So because it's meso, it will not have an enantiomeric pair, because as we saw in the previous example, it would just be, the molecule would just be identical. So therefore, the only option that we have left is the trans version, or the one that has a dash and a wedge. Now, let's look at this molecule, assess the absolute configuration. So we have highest priority, second, third. That looks like R because it's going clockwise. The hydrogen is in the back, so it is R. And notice that this is exactly the same as here, so it should be the same at that chiral center specifically. Then if we move here now, we would expect this one to be R because it should be the opposite of this position here, because our dash, we've converted our wedge to a dash. Now, let's do it anyway to be consistent. So this is our highest priority, second, third. That looks like S, but the hydrogen is in the front, so it's actually R. So this is RR and not meso. So the enantiomeric pair would be these two, where we have the dash and wedge switching spots. So here is the molecule that we just assessed as RR, and its enantiomer would be this one, which is SS. Right? So here is RR. This must be SS. We'll do a quick check just to confirm. So this is the highest priority. This is second. This is third. That looks like S. The hydrogen is in the back, so it is S. Here's the highest priority. This is second, and that one is third. That looks like R. The hydrogen is in the front, so it is, in fact, S. You have to switch. So here again is the only enantiomeric pair for the starting molecule because of this tricky idea of meso. The meso compound eliminates one set of enantiomers that you would expect. So hopefully this shed some light on the meso compound idea. I hope you benefited from the video and learned something. If you did, please leave a like and subscribe to the channel for more content like this. If you have a topic idea that you'd like me to cover or any specific questions, please leave them down in the comment section and I will get to them as quick as I can. So with that, I will see you all in the next video and I hope you have a great day.